Hey everybody, we are live on YouTube. So we've got, I bring up some 201 here. If you're here and you got questions, let us know. I bring up 201. But if you are here in the chat, let us know and let us know which questions you have. Right now, 201, always good to do some 201 questions, but I'd hit the wrong button. Let's see, no one's here yet. No one's saying anything yet. Maybe Calzone will visit us today. Who knows? Bscape will visit us. You never know who's going to come and visit during office hours. Let's see. Maybe we'll do a new 201 assignment. You know what? Chapter 15 homework might be pretty interesting. Chapter 15 homework. Something we didn't do yesterday. So this is homework material for what we did yesterday. We'll see if anyone's chatting here. No one said anything yet. But let's head over here to the main screen. Let's do it. You know, it's Throwback Thursdays. Let's sit back and let Crash bring us over here on these Throwback Thursdays. Crash, bring us over here on these Throwback Thursdays. Do it, Crash. You got it. Let's do this. Throwback Thursdays. Class is not over yet. Gotta remember to take that down at the end of class. So what we see right here is a dictator is concerned about his negatives. That is the percent of country's respondents, residents who express disapproval of job performance. His political committee pays for a series of TV ads, hopes that they can keep the negatives below 41%. And they use ads, they use polls to find out how effective this has been, and let P be the proportion of the country's residents who express disapproval of the dictator's performance. The dictator probably doesn't care about that. I think it changes what it is in different versions of this question, but there's something we should know. And we should know how to write the null, and we should know how to write the alternative with my 10,000 word documents open. We should know how to write the null, and we should know how to write the alternative. Now, when you write out the null hypothesis, this is the one we should know how to write first. The null hypothesis is going to have, let's go right here, it's going to be HO for the null hypothesis, and then we're going to have a population parameter right here. And then we'll have equals, always has the equal sign. And then we have hypothesized value. This is how we write the null. Now, the alternative is really easy to write. We just go right here and we change the sign to either less than, greater than, or I got to go to the insert right here, the not equal to. So all we do is we change the sign. So it'll be one of these three signs. Let's go a little bit smaller on the font. It'll be one of these three signs right here. So here is the null, and we need to change the O to an A right here for the alternative. Wrong way. There we go. We have the null and we have the alternative. Now you might say this looks nothing like we're doing in this problem. Well, you're kind of right. We need to figure out what the population parameter is. The only values that go into population parameter for our class will be either P, mu, or mu1 minus mu2. So the first one right here is for the proportion. When we talk about, you know, whether people approve or disapprove of something, if people own a cat or don't own a cat, if people like Taco Bell or not like Taco Bell. Favorite example right there. The second one is for quantitative numbers. When we talk about the true mean height of individuals, the true mean GPA of individuals, the true mean distance somebody drives, the average distance many people drive to school. These are all quantitative. The last one here is for the difference between two quantitative values, because it's mean 1 minus mean 2. And so this would be the true mean difference between people who live on campus and off campus from how far they live from school, the true mean difference for people's grades who study before the test and people's grades who don't study before the test, the true mean difference in age of, let's say, graduate students and undergrad students. So you can take two groups right here. We have undergrad students and graduate students, and we're looking at the difference in a quantitative variable. So the last one right there is the difference in quantitative variables. Very important. We know that right here. The hypothesized value. The hypothesized value is anything we want it to be. Now, there are constraints because I said anything and then I immediately backed off of that. Because if you're doing proportions, proportions can only be from 0 to 1. So if you're doing the proportion, you can only hypothesize a proportion between 0 and 1. And so if you notice right here, when we do our problem, I think they were saying 44% was the hypothesized amount, and the null has the equal sign. The null must have the equal sign, because we're seeing if the dictator's negatives are equal to 40%, or if there's evidence that the campaign has made them less than 40%. And a lot of good practice right here, as long as you know the null has the equal sign, we always say that the null has the equal sign. You go back to your problem, it was 41, but still we're trying to lower their negatives, and we've done it. So the next one is a 4-section spinner fair? So if the 4-section spinner is fair, we should see 1/4. But think about this. If it's not fair, what would we see? If it's not fair, we'll go to our last Word document right here. So we have 1/4 right here, which is the proportion, what we hypothesize would be true. So we'd assume that it'd be equal to 1/4 of the time. That's what we hypothesize would be true. But if it's not fair, well, then it would be not equal to that, because either it's fair or not fair. So we're seeing if there's evidence, and the alternative is the evidence-based claim. We're seeing if there's evidence that the true proportion of time that the spinner comes up with this one spot is not equal to 1/4. And so not equal here for the alternative, which is the evidence-based claim, and the null has the equal sign. The null has the equal sign. So guess what? Null has the equal sign. We don't even have to guess. We don't even have to think about it. The null has the equal sign. Only 28% of people who try to quit smoking succeed, and this motivational tape says it can help people. So if the motivational tape says it can help people, they're making a claim right there. So only 28% of people who try to quit smoking succeed. So we'd expect by random chance, you know what's happening right there. We'd expect by random chance to see 28% of people quit smoking succeed. But if this motivational tape helps, then the true proportion, and notice how we read this. We're looking for evidence for the alternative that the true proportion of people who quit smoking is greater than 28%. The null states that the true proportion of people who quit smoking would be equal to 28%. Is there evidence that the true proportion of people who quit smoking is greater than 28%? And this is really some good practice on writing your nulls and your alternatives. Make sure to try to do it without the help of looking at the answers, just to practice. Then you'll know the null has the equal sign, and we can kind of do that every time. So this one's another pretty easy one. So far, this homework's been pretty easy, like no numeric entries. Those are the harder ones. This one is just interpreting a p-value. And a p-value is, we should decently know this definition. A p-value. P-value. The probability of observing our results more extreme, occurring by random chance variation, given that the null is true. There we go. This is the p-value, the probability of our results more extreme occurring by random chance variation, given that the null is true. So we'll look at the definition here in a moment, but there's two ways to think about p-values, generally speaking. P-values are either generally very small, and by very small, don't do that. Good. By very small, we mean less than 0.05. That's small, or they're very large. So when you have p-values, you have this point right here, 0.05, which is generally assumed to be alpha. Alpha can be moved. We can say, okay, let's bring alpha, over. I can't grab it though. Let's move alpha over to here. I don't like doing that. Hey, what's up, Jing Yang? Feel free to ask a question. We're just doing a little tool one, but whichever question you're working on, feel free to ask, and we will work on that. You got it. So alpha is the point at which we reject the null. 0.05 is generally when we say things are statistically significant, like that's the practice among statisticians. And so I want us to think about what we're saying here is we are going to assume the null is true. Can you work on 1D? I think question 320, right, Ting Yang? Is that 320? Remind me if it's 320. I think you're in 320, right? BS 320, you got it. We'll do that one next. You got it. So with this right here, we're talking about statistical significance with p-values. This is good stuff for 320, right, Ting Yang? So we have here that it is statistically significant if the p-value is below 0.05. 0.05 exactly is not statistically significant. It needs to be below 0.05. And when something is statistically significant because of low p-value, then that means it's unlikely by random chance. So what all does that mean? And what's an example of it? So many p-values in 320, so many, you see them all the time. It's like, okay, well, this is unlikely by random chance, what we observed. And I want you to think here, let's like do an example from 320 to make it kind of work. If we were to have people's relationship between height and weight, what would you expect if there's the null for height and weight is that there's no relationship between them. The null for height and weight, that's fine. The null for height and weight is that there's no relationship between the two variables. So how should it look? If height and weight have no relationship, then how would this look? If height and weight have no relationship, then it would look random. It would just look random. There'd be no relationship. Because what is likely to see? What would be likely to see if the null is true? If there's no relationship between height and weight, which is the null hypothesis, then what would be likely to see? This would be likely to see. If there's no relationship, what would be unlikely to see? And this is a very strong linear relationship right here. So what we observe right here is very unlikely on the low p-value side. Let's try another example right here. Let's do one kind of more related to our class. If we have here the null hypothesis that, so this is the second example, we have here a null that Brian's average mile time is equal to 6 minutes. And the alternative is that Brian's mile time is not equal to 6 minutes. So if the null is true, what would lead to a very high p-value? If the null is true, what would lead to a very high p-value? What would we expect to see given the null is true? Like what values of Brian running his miles would lead to very high p-values? So you have to think, what would be a likely result given the null is true? What results, or result just as extreme of it, would be very likely given the null is true? So look at the null hypothesis and think, if that's true, what would I expect to see? If that's true. So if Brian runs his miles in 6 minutes, what would be likely to see? What would lead to a high p-value? Something that's very likely to see given the null is true. What would I run my miles in? No one knows? Oh, no. I might have to answer it. The answer is, something like 6 minutes. Something like 6 minutes right there. 6 minutes would be very likely to see, or maybe 6 minutes, 6.2 minutes. It's like 6 minutes, 12 seconds. But this would be very likely given the null is true. But what would not be likely, maybe I run my miles in 9.5 minutes. So think about this. If I run my miles in 9.5 minutes, what would you do to the null hypothesis? If I run my miles in 9.5 minutes, you would reject the null. You'd say, I have evidence that Brian is not a 6-minute mile runner. So me running my miles in 9.5 minutes is evidence I'm not a 9.5-minute mile runner, because 9.5 minutes was what, given Brian is a 6-minute mile runner? It was unlikely. It's unlikely that I'd run my miles in 9.5 minutes, given. And so you see here the probability of observing Brian running his miles in 9.5 minutes or more extreme times by random chance, given Brian is a 6-minute mile runner, is very, very unlikely. Reverse that to where we do not reject the null. We fail to reject the null over here for this example. And you can see here, we do not reject the null because in this instance, it'd probably be closer to here. We'd have a p-value right here or so of like 0.8, because Brian running his miles in 6 minutes, 0.2, is very likely given the null is true. So we don't reject the null. You say, well, yeah, that seems in line with what the null is. This seems likely. It seems probable. So when you look at the p-value, it's a conditional probability. It's what is the probability of these results given the null is true? So very, very important stuff right there. So there it is. And we got it. Long answer for a very short question. Let's hop over to 320 right here. I'm going to pull up the 320 question. Let me go grab the 320 assignment. 320, I hear 1D for 320. They have an assignment due tonight. 1D for 320. Maybe I did too much of 201 yesterday because they seem to be good. Like we got the video for yesterday, and you put the stamps in it, Brian. So I went in, and this week I've been really on top of it by putting in all the stamps. I have to go back and pretty much rewatch the video. So I get to watch myself reteach the lecture. And in doing so, I put in the timestamps. I obviously don't watch it from start to finish. I skim the video. It'd be really boring if I watched the whole video. Because I teach it. I know what's going on. I know the class. Oh, okay, cool. Okay, so this one, let me put a huge note right here. So you have to watch another video. So for this help right here, I'm not going to solve the polynomial orders, but so Tingyan, did you do this one right here, Tingyan? We did this problem on Tuesday. Maybe we did it yesterday. I think we did it on Tuesday. In like Tuesday's video, we did this problem where we figured out the polynomial order. So you have to know the polynomial order for this model. You have to know the polynomial order. Once you know the polynomial order, you can go in here and replace these numbers So I'm putting in a huge disclaimer that hopefully people see this. So solve for the polynomial orders first. You have to solve for these. So like solve these. You have to solve for these first right here. And then we're going to go to the polynomial order. And we're going to put the numbers into here that we found. So we're going to put in some numbers we found. And I'm going to say we're going to pretend that you found these. And then we create the polynomial order model. So this has now created a polynomial order model. I can't stress this enough. You need to go in and solve for these numbers, though. I did not actually find the numbers for you right now, but I can do those parts if you want. But this right here creates the polynomial order, and we can run a check regression on it. So, Tingen, were you asking about this right here? Fit a model with the polynomial order with the relevant polynomial terms, report the R-squared adjusted and the RMSE of the model, and compare them to the model in B. Comment on whether these extra terms have significantly improved the model. Okay, yes, that's, I think, what we need to talk about. Okay, so the model in model B is just going to be fuel efficiency tilde dot. So let's go here to model B and m dot B tilde dot, comma, data equals, and the data set is auto. And let's go here to summary. So, oh, we're inside of something still. Oh, this never ran because of that. Auto not found. Data auto. And so there's the model B. And otherwise, if you haven't this week, will you work on the problem towards the end that are interpreting the graphs about how the party size? Yeah, you bet, Timothy. We'll do that right here. We got it. Otherwise, I'm going to watch the video later. Yeah, let's do that. We'll do that next here. I'll explain this right here. And let's look at the polynomial model. This is not the right polynomial model. Like, I can't state that enough. Someone's going to use this model. I'll be like, why'd you use this model? So when you look at this model right here, what we need to look at, and I think we can do this. Will this work? No. That's such a bummer. So the RMSE, let's take a note on it. Here's the RMSE. And we'll put both RMSEs next to each other so we can view them together. Here's the, did I grab the RMSE? This is the R-squared adjusted. Yeah, so I think I grabbed R-squared adjusted instead. So here's the R-squared adjusted for model 1, model 2. R-squared adjusted. And RMSE. And what's going on with these right here? What do the signs point to, Timothy, right here with these? Here's model 1. Here's model 2. And what do you notice going on with these models? So this is model 1 right here. And this is model 2. So, and then you have the R-squared adjusted for each model, and you have the RMSE for each model. What do you notice? And these are different from your models, because my model 2 is not the right model. But what do you notice about the RMSE when you go to the polynomial model? Even with my polynomial model I made, which is not the right model. So the RMSE is the typical miss the model makes when it makes predictions. And it's also going to take into effect that we have more variables in the model. So the RMSE actually goes where? Going from model 1 to model 2, and this is the poly model. So let's put poly next to it. And let's just call this simple. Or like all variables. That's good right there. Model 2 is improved on both, exactly. And I'd try to be specific, saying, you know, the RMSE has decreased from this to this, like by a measure of about this amount. The R-squared adjusted, which controls for how many variables are in the model, has also gone up, which is a good thing. So you want RMSE to go down because RMSE is typical miss. So the typical miss is smaller. It's also weighted for how many variables in the model. And the R-squared adjusted has gone up, which is a good thing because that's weighted by how many variables are in the model too. So by all intents and purposes, the polynomial model is doing better. Oh, no worries. Oh, no. Oh, yeah, Timothy, then don't worry, man. Just, yeah, if you want to just listen up or come back and watch later, that's excellent. Or drop in something that you want me to look at. You were talking about the tip with the bill size and stuff like that. So let me go down here to this one you're talking about, and let's talk about it a little bit here. I think this one has the interaction, right? Use tips. There we go. The percent tip left on the bill, tip percentage has an interesting relationship with bill amount and number of people at the party. So let's load in the data frame. There we go. Fit a model predicting tip percentage from the bill amount and party size. Include the interaction. Cool. Yeah, no worries. Awesome stuff right there. So, and then we'll do the C interactions. I think there's a lot of output for this. People are asking, how much output is there for all of this? And there can be a lot. It can be a lot of output. So people are like, I had a 28-page project. And I'm like, well, let me check. Let me check. We're going to predict tip percentage by bill and party size. Here we go. There we go. And data equals tips. Go away. Good. C interactions and model, comma, extra. Ooh, is this supposed to be many? It's supposed to be many. Will extra equal true work? What if I do extra equal true? What will it do? That's not good. And let's remake it. Decrease font size. There we go. And so with this, and you can also do the visualize model on this. Visualize model works also. I kind of like visualize model better. Visualize model will create the lines right here and it'll give them colors. Now, one person was wondering, I got an email and it's a good question. I think it was a Discord message actually. They said party size small is not on here. So you'll notice there is no party size small line, but it's actually there. It's just overlapping with another one. Why can you only see two? Exactly, that's what it is. What it is, when we do these predictions for party size small, I think it uses the 5th percentile, and this is the 50th, and this is the 95th. So if we go to party size, the variable party size, when it plugs in a small value for party size, it goes to the quantile of tips $party size, and it asks for the 5th right there, and that's 2. And then when it goes to a medium, it plugs in the 50th percentile, and that's 2. So party size is so skewed. It's a right skewed data set. We can look at it right here with the histogram. We need to delete this off. But party size is so skewed to the right. You can see by my right here that this is the 5th percentile, and this is also the 50th percentile. So because there's an overlap of the 5th and the 50th percentile, it doesn't actually make a smallest line. They're overlapping, the two lines. I think it made the smallest line, and then it plotted the medium line on top of it. So a small party is 2, and a medium party is 2, probably because a lot of people go to a restaurant with 2 people. So you can think most business at a restaurant is 2 people walking in saying, let's get lunch. I used to go to a restaurant all the time by myself. You know what? Restaurants are expensive. You see, I ate like $1 or $2 a day for lunch for food, and if I go to a restaurant, I'll spend like $10 or $12. You do that every day, that's $4,000 a year. So that's an expensive habit to go to lunch every day. So lunch every day, $10 a day, $4,000 a year. Got to watch out. 2020 made it so I'm not really doing that much though. So what we have right here, let's see what the questions ask. Would we be justified in dropping party size term from the model? Okay. So let's see, and then you'll see the interaction is significant, party size is not. So Timothy, well, you probably know this. Don't worry, you can keep working out. If we see that party size is not significant, which it shouldn't be according to the instructions. If we see if party size is not significant, which it's not. Party size is not significant, but removing it will violate model hierarchy, which is not the end of the world. Like literally, this is the discussion people need to have. It's like, well, we have in this model, we have inside this model party size and bill. And then we have right here the party size bill interaction. So we have party size bill and the party size bill interaction. If we remove out, I think it was party size, right? You violate model hierarchy. Because to have the two-level categorical, or to have the two-way interaction, you're supposed to have these single-order terms. And so by removing out party size, you violate model hierarchy. You kind of don't want to do that. I mean, you can do anything. It's ill-advised. If someone says, can we do this? The answer is yes. Should we do this? Then the answer is maybe not. So let's look at the specifics of the question. I think the question says, Would we be justified in dropping party size? You could say it doesn't bring with it new information. The parts I was unsure about is this question is whether it's interpretive negative and weak or strong positive. You wouldn't mind. Yeah. Does interpretation go right here? Write out the overall regression equations. We could do that next. Next, write the implicit regression equations with 1 and 4. Yep, we can do that. We did those a lot in class. What is the story the data tells us? In other words, describe the relationship of tip percent. Yeah, this is it. Okay. This is the question right here. So I'll make sure to try to mark this. I'm going to put like a highlighter and be like, Brian, here's the point when we're talking about 2D right here, or 3D. So the way this one works right here. Well, let's look at this. We want to talk about describe how the relationship of tip percentage and bill amount change as party size gets bigger. So let's look at this one right here. So the blue line and the black line are on top of each other right here. So we have a medium line right here, and we have the large right here, the medium and the large. So as party size increases, the slope of the line gets less what? As party size increases, the slope of the line gets less what? As party size increases, the slope of the line gets less. You're really good at typing things you've typed on. You're the only person here I'm talking to, Tim. So you're, it gets less. You can see the black line, and then we make it larger. It's going to get less negative. So do you see how we go from the black line right here, and that's a medium, and then when you go to large, which means party size increases, it's getting less negative. So when you go from a medium to a large party size, the line gets less negative, which means the relationship's getting weaker, because the more flat the line is, the weaker it is. So you can see right here, as party size is increasing, the impact of bill on tip percentage becomes less negative and weaker. It's going towards 0. The blue line's also here, so just you see the increase of party size is making the line weaker and less negative. So there is a weaker relationship between bill and tip percentage for larger party sizes. Does that make sense, Timothy? As you see, the line from black to red goes up more vertically, so it's getting less negative and weaker. Yeah, exactly. You can say, yeah, it's less negative. Yeah, it's weaker, because you can say, yeah, if it were to become more negative, you could say more positive. Yeah, because it could get more positive and stronger if the line was already going up. And so it just depends on how you want to describe it. But the relationship is weaker for larger party sizes. We see that bill has less of an impact due to the line becoming less negative or more positive, whatever people want to say. But just kind of, look at the line and be like, okay, what's happening as we increase this? And you have to be like, okay, here's the line, and then here's the new line. You have to kind of compare them and say it's getting less negative and weaker. So there we go. That's it. I think that's excellent right there. Let's see what else. A better predictor might be the bill per person. So you're welcome, Tim. Great job. This is variable creation right here. We're going to make a bill per person, which is going to be dividing the bill divided by party size. So bill divided by party size. So we need to go and divide bill by party size to make a new variable. So bill per person. And we're going to go here to tip. And then bill divided by tip. And party size, and there it is. Now, what we can do is we can take this variable right here and append it onto the data frame. So what we've done is we've made up a new variable. It's just a vector of data. Then we've taken the variable and appended it onto the data frame. So you can write the variable to the data frame. Yep, you're right. I don't think it does. So define a variable, blah, 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 and add it to the tips data frame, then make a symbol predicting tip percentage from it, examine the summary. Yeah, and we're only using this variable, right? I think this variable is pretty bad. Like here, we'll predict tip percentage from it. So LM, there we go, and then bill per person, data equals trips. What? There we go, and let's look at the summary and the model. It doesn't do as well. I think if you look at this, the variable right here explains 10% of the variation. And previously, if we look at our previous model right here, so we have 10% of the variation explained right about. And in the previous model, we need to look at the summary of it now. We had 14% of the variation explained. And still we have a better R-squared adjusted, typical miss of 5.7, typical miss of 5.8. So using model comparison metrics of RMSE, the typical miss the bill per person model makes is 5.8. the typical miss that the interaction model makes is 5.7. So you can see right here, this model is doing better on RMSE, and then R squared adjusted also 12.74. You want this to be higher, and this one is higher, the 12.74. So hopefully that's kind of making sense right there, how to compare your models. And that's one of the big things we're kind of doing this assignment is we're making a model, looking at how it does, and asking, is this model better than this other model? So that's got all of that right there. Might go back and do a little bit more. 201 coming up right here. 201, so much 201. Let's do it. Let's get 201 going. Where'd 201 go? What's down here? I'm glad the homework has gotten more manageable without having to watch the office hours. Yeah. Oh, Timothy, you're welcome. Yeah, I just think it's like this. We always say this, and next semester, come in and talk to 320 and say it gets easier. It gets easier. Be like, you know what? It's like a ball rolling. If you start practicing, if you get down your R skills, the course really gets easier and more manageable. The assignments don't feel that long. I mean, we probably just did a third of the assignment in 20 minutes. But if you understand, and it's a lot of repetitive stuff, we're trying to build a skill set here and we're just sharpening your tools. So great job, Timothy. I think you're on track. It's just, sometimes people ask me, they'll be like, are we just doing the same thing over again? I'm like, well, yeah, kind of, but we're changing this. If you notice indicator variables, did indicator variables feel like a lot of new material this week? I mean, all we really did was learn how to put categorical variables into a model. So this whole week we were just talking about, hey, here's how we put a categorical variable in a model. Here's how we assess it. Eat some Triscuits and need some water. So we went through just really one idea, but we talked about all the ins and outs. Guzzy, good to see you here. For the homework tonight in Session 1, how do you do the one where it says Nutrition Laboratory? Yeah, let's do it. I've got to pull up that one. I've got another homework thing open. So let's pull up the Nutrition Laboratory one. Is it the hot dogs Nutrition Laboratory? Or is it yogurt? Let's see. Is it the homework one, did you say? Let me see here. For the homework tonight in Session 1, yay, we got so many people here. Yeah, we just coded the info to fit. Yeah, what we're all doing. It's already doing. You're right. It's just practice. It really takes a lot of practice, though. I think that's one of the hardest things is practice. And then you get it down, and you're like, we're good to go. Here we go. And let's do it. Okay. So, sorry. Okay. So for this problem right here, we are going to make a confidence interval for the true mean. So let's go ahead and take our notation. So with the notation, I need people's help right here. I need your help. What is one bit of notation in this problem? I need one bit of notation. So we're going to solve all the notation right here first. What is any of this notation? What is any of this notation? Someone's got to help me get one bit of this notation. Any bit of the notation. Nice job right there. That's the standard deviation. Great job, Gussie. 1,000 points, everybody. Everyone being here. Points going crazy. Mubot's tracking all the points. Mubot, are you here? Nice job. That's the mean. Exactly. Let's see if Mubot is here. Yes, Mubot is here. Mubot's always here. And so this is the mean, which is the sample mean, because this is the sample size. And this is going to give us our confidence level. And we need to find the t statistic. So when we're making a t interval, we need to know the equation is y bar plus or minus t with n minus 1 degrees of freedom, s over square root of n. So, yep, nice job, Timothy. Get to that gold tier. End of the semester, get to the gold tier. So what do we not have right now? We do not have t, but we can find the degrees of freedom. So the degrees of freedom are n minus 1, and it'll be 59 degrees of freedom. Now, what do the degrees of freedom tell us? Oh, my Triscuits are killing me. Not literally, hopefully. I'm going to need to get some more water. Okay. So we have to go to a site like statdistributions.com, or we have to use a t-table. I am not fans of t-tables. I am not a fan of t-tables. T-tables are just these applets, but you have to look up the numbers. We found out that there was 59 degrees of freedom, and we want to make a 95% confidence interval. So we're going to plot the middle 95%. So the middle 95% is plotted right here. The t for a 95% confidence interval with 59 degrees of freedom is 2.001. And I put it in the chat right there, so you can go to this site. You want to use the between when making a confidence interval. You can also do it with this. The right number is there because 5% on the outside, 95% on the inside, or rather, I like to do it 95% on the inside. So 2.001 is our t statistic, and we've just marked all the notation. So t with 59 degrees of freedom is equal to 2.001. So that is it right there. And then let's go ahead and start putting in the numbers. Let us start solving the numbers. The mean here is 322. The t is 2.001. The standard deviation is 37. Sample size is 60. And we're going to solve for the margin of error first. The margin of error is going to be square root of 60. 37 divided by that. Times that by 2.001. And that's the margin of error, 9.56. So plus or minus. There we go. There is our interval, 322 plus or minus the margin of error. So 322 plus, 9.56. 322 plus 9.56. 33156. And 322 minus 9.56. 312.44. Should do it. Yes. Now, this is maybe the most confusing part of this problem when they do the conditions. Condition 1 is random. We randomly select these hot dogs. Condition 2 is these hot dogs are less than 10% of all hot dogs. Condition 3 is that it's a nearly normal distribution. So we are going to assume that these hot dogs are independent and are from a normal distribution. This is the assumption here. We're good. So that's basically nearly normal. Next, we have randomization. We don't know. I wish the problem was more specific, but we don't really know. But we're going to assume, bad thing to do right there. Now, the 10% condition we know is met. Why do we know that the 10% condition is met? 10% is that we sample less than 10% of all hot dogs that exist. If there's less than 600 hot dogs in the world, we are all done. We're all done. These hot dogs are way less than 10%, and you just have to know that the 10% condition means this sample right here, the sample of 60 hot dogs needs to be less than 10% of all hot dogs. And I'd say for certain it is. This question was just created for me to say hot dog with my New York accent. Even we're in New York today. New York. So is the nearly normal condition satisfied? We don't know. We'd have to look at the shape of the distribution, but unless the distribution is heavily skewed. So a full answer would say, we don't know, but unless the distribution is heavily skewed, a sample size of 60 should be good to proceed. If it was heavily skewed, we needed a sample size of at least 100. So we're good on that. Last but not least, we're going to interpret the interval. And I never like their interpretations. Let's go back to ours. So when we do our interpretations, we want to do I am blank percent confident that the true blank is contained in the interval blank to blank. I am blank percent confident that the true blank is contained in the interval blank to blank. And so this is what we have going on right here. I am 95% confident that the true mean sodium content of the hot dogs is contained in the interval, and then 311 to or 312 to 332, the numbers we obtain on the first part of the problem. So we look at the interpretations here. We are 95% confident that the true mean content of these sodium hot dogs is contained in the interval. So that is basically what we were saying. Gussie, do you have additional questions? Which ones are you working on? Let me know. We will work on more questions right here. I'm going to bring up the old assignments right here. Let's see. Bring up the old assignments. And where is it at? Went to the wrong thing right here. So many tabs. Here we go, Pearson. And let's see, what questions are people asking? Part B on the one you're on? Okay, cool. Yeah, let's do this one. Okay. So part B might be the interval itself. Let's see, all the assumptions and conditions are met. Random, 10%, nearly normal. Good to go. And so where people usually get stuck is they usually get stuck on finding the t-statistic. I find that that's usually the biggest problem. How many degrees of freedom are there on this problem, Gussie? How many degrees of freedom are there? So how many degrees of freedom does this have right here? This question right here has how many degrees of freedom? What are the degrees of freedom for this problem? Since this is a one sample t, with a one sample t, we'd have n minus 1 degrees of freedom. So how many degrees of freedom are there? And the degrees of freedom tell us which t we're going to use. So how many degrees of freedom are there? Yep. That's what we'll do. And how many degrees of freedom are there for this problem? So which t are we using? A t with this many degrees of freedom. How many degrees of freedom would there be on this problem? Because we'll go to the website here in just a second. How many degrees of freedom would there be? We have here the sample size, the sample mean, and the standard deviation. So there would be how many degrees of freedom? Let's see what people say. The degrees of freedom will be n minus 1. So we need to figure out how many degrees of freedom, because that'll tell us which t we're using. And we want to make a 99% confidence interval. We want to make a 99% confidence interval for the mean. You're right. Nice job, Gussie, right there. 71 degrees of freedom. So we go over here. We put in 71 degrees of freedom. Then we put in 99 for the confidence. I'll put this here in the chat again to make sure everyone sees it. And there's our t-statistic. Our t-statistic is 2.647. 2.647. So we're going to copy the problem right here, just this part. We're going to remember in our heads 2.647. So the degrees of freedom were 71, and the t-statistic with 71 degrees of freedom was 2.647. So now that we have everything, we just plug it into the formula, y bar plus or minus a t with 71 degrees of freedom, which is n minus 1. So we'll just write it as it is. And then we do s over square root of n right there. And so let's give it a shot. The sample mean is 23.9722, a lot of decimals, plus or minus the t, which is 2.647. And then we do the standard deviation of 2.40347 divided by the square root of 72. There we go. And so let's go ahead and start solving this. We go here, we do 72 square root 2.40347 divided by that. We times that by 2.647, and there's that. And we basically have it. So that's 0.75, so 23.9722 plus or minus 0.75 when rounded. And I think it's going to want 2 decimals. But I think that's got it. Let's go back here and 2 decimals. So we go and copy it. 23.9722 plus this, 24.72. And then we go 23.9722 minus this, 23.22. As long as we entered the numbers in the right way, we did. Awesome. And then we interpret the interval. I am 95% confident that the true proportion of flights that arrive on time or the true percent of times, sorry, I shouldn't say true proportion, but the 2% of times that arrive on time each month is contained in the interval. And we see right here, we are 95% confident that the true proportion of flights that arrive on time, or the true percentage, true monthly percentage. I shouldn't say true proportion. It's the true monthly percentage, because each month they're looking at, what percent of the times are the flights arriving on time. I think they're doing daily. So each month from 2001 to 2006, consider this to be a representative sample of all months. There is no evidence of a time trend. Yeah, that's got it. So that's got the flights arriving on time. Are there other problems you were wondering about? Which ones were you wondering about? Go back. Get the data here. Which ones were people wondering about? Here. Let's see. Ask questions if you got them. Let me go grab the other. We got time for one more, I think. Easily time. Good. Oh, close that out. I was like, why did I close that out? Because I'm switching assignments right now. It's like, why would it do that? I think we got through question 2. We got to question 3. It's more on hypothesis testing right here. Oh, we're going to do a full hypothesis test. That's awesome. So this is going to be a full hypothesis test. And let's take a look. An organization monitors many aspects of elementary school and secondary education nationwide. There are 1999 numbers, back when I was in high school, are often used as a baseline to assess changes. In 1999, 35% of students had not been absent from school even once during the previous year. In 2003, responses for 8,818 randomly selected students showed that this figure had slipped to 34%. Officials, of course, would be concerned if students' attendance were declining. Do these figures give evidence of a change? Now, this is where people get confused on this problem. This is where we're talking about the evidence. Is there evidence of a change? Is there evidence of a change? Now, everyone should know the null has the equal sign. We review that a lot. The null has the equal sign. Please watch the first problem. I think it was back here where we talked about how to write nulls and alternatives. And the null always has the equal sign. The hypothesized value goes here, and the parameter of interest that we're talking about goes here. And so review the first problem where we talked about how to write nulls and alternatives. They're looking for evidence of a change. That's the evidence they're looking for. So they're going to look to see if it's different. So the key right there is, has it changed? Condition 1 is random, which encompasses random and independent. So as long as they randomly select these people, which is plausible, then it's justified. 10% means they take less than 10% of all students nationwide, so that's believable. And success failure condition means we have at least 10 successes and at least 10 failures. We'll go into this more next time, but we've been doing this a lot. We need at least 10 successes, at least 10 failures, given the null is true. So 35 right here is the null, and we have a sample of 8,818. So let's see, 35% of 8818, and that's that. Now we need to do P0, 65% of 8818. And what we're doing right here, let's show it visually. We're literally seeing that NP0 is greater than or equal to 10, and NQ0 is greater than or equal to 10. This is the success failure condition to make sure we have at least enough successes and at least enough failures. So we are good to go there. All of those are satisfied. Perform the test and find the p-value. Okay, let's go ahead and grab the data right here and do the test and get the p-value. So to get the p-value, we need to know the equation we're going to use. The equation we're going to use will be z-score is equal to p hat, which is the observed sample proportion, minus the hypothesized proportion over p0 q0 over n square root. This is a one proportion z-test, and we need to identify our notation now. So always sit down and identify all of your notation before working the problem. We might have skipped a step there, but I think we have everything we need right here. Here's the sample size. Here is the hypothesized proportion right here. That's the hypothesized in the past, which means we can get Q0 is equal to 0.65 because Q0 is the complement of P0. P hat is equal to this right here. So from here, we're going to simply just plug in after we identify the portions of the problem. So 34 goes right here. That is the p hat, what we observe. 35% is what is hypothesized to be true. This is the hypothesized. This is the complement of the hypothesized. And then this is the sample size right here. And we're going to get the z-score. So the z-score is going to be the standardized difference between what we observe in the sample and also what we have as the hypothesized amount. So the bottom of this is going to be 0.35 times 0.65 divided by 8818. and then we square root it. We're going to take, so that's going to be negative, whoops. So 0.34 minus 0.35, negative 0.01, divide by, and z-score is going to be like 1.96. Yes. This makes solving the last part of this really easy. It's basically negative 1.97. So with it being negative 1.97, many of you might already know, if you've done a lot of these problems, that if we're going to be, I'll make someone a stat1 legend if they tell me the p-value right now, because we don't even have to go to David M. Lane to solve this. If someone can tell me the p-value for this, which you should be able to figure out very quickly. Someone's watching this video later and be like, oh, I know it. They're like, oh, I got this. The p-value should be pretty easy to figure out right here, but don't worry if you don't know it. It's all right. There's a trick, because that's the z-score, and then this is just as extreme as the z-score. So we'll go to David M. Lane. Let's go to David M. Lane right here and go and see the answer. You're like, do you know it, Brian? I promise you I do. Because it's 1.96 is as famous as it gets in statistics, even so that the applet even already basically has it entered in. So just so you know, I'll put it in here in a second, but the z-score is negative 1.97. Is that rounded enough? And then the p-value is going to be, how many decimals does it want? 3 decimals, 0.49, I think. 0.49, yeah, it's got it. Because the reason I knew this, just to explain how did I know this, it's because if we do this, which looks a lot like the graphic I drew, so if you look at my graphic and the graphic on the screen right here, if it's 1.96, the p-value is 0.05. But we're not at 1.96. We are outside of this number, which is so close to it. And I actually got it down to the third decimal, or the fourth or fifth decimal, because it's right there. 1.96 is classically 5%. And then I was like, okay, it's just a little bit further over. It's basically 1.97. So with that, I was able to estimate it's just a tiny bit less than 5%, just a tiny, tiny bit. So you can sometimes get these if you know the empirical rule well enough, if you know the 68, 95, 99.7, and we are using a z-score right now. So then it uses an alpha right here, which is when we reject the null. We've got some really good notes on that from today. We were talking over here about rejecting the null when it's less than alpha. So we landed, it's using a different alpha, which I think I can delete that. They're saying right here, use an alpha equal to this. This is what their alpha is equal to. So they're going to reject in this region. And we landed right here. So since our p-value is at 0.049, the p-value is less than alpha. This is the rejection region, and we are thus going to reject the null because our p-value is less than alpha. So let's take a look right here. We reject the null. There is evidence to conclude that it has changed. Note the wording right here. We reject the null when the p-value is less than alpha. This means there is evidence for the alternative, which is that the perfect attendance has, or the attendance has changed. So we should be good to go. That's got it. I am not sure if you have already done this because I just hopped on, but you come into deviceable statistics of twins. That might be the next one. Let's do it. Wait, there's more? There's more? Do you think this difference is meaningful? Nah, it's like 1%. It's probably not meaningful, quite small. So even if there are statistically significant, probably not much. Perfect. Perfect time, Macy. Perfect time. So let's do the vital twins one. You ready? Okay, so Macy, help me out here. Identify some of the notation in this problem. Identify some of the notation in this problem. We need some of the notation being identified here. You probably can't see it yet. So 17 sets of twins for 500. So up, yep. And so this is going to be born to, so let's see. They're only going to use, okay, there we go. So this is the tricky part. What is the 17 sets of twins in notation? And what is the 422 girls? So what is the 17 sets of twins and what is the 422? Or what for yours, what is the 17 and 520? So what are those in notation? It's a tricky one. Or I'll put everything here we need to identify. So let's start identifying these. Oh, that's a good question. I've got try to identify anything on the screen right now. N is 520. Yep, boom. Got one down. So there's 520. That's N. Okay, so we know this is going to be this. We're getting closer. So we're on our way. Do one more and I'll do the rest. Even if you're wrong, it's all right. What's up, Dana? This is the homework, which has a lot of similarities. This is the homework, which has a lot of similarities. And I'm trying to think when it's... This is not the one that's due tonight, though. This is the one that's due next, though. We did some of the ones from tonight, though, earlier. We did the hot dog one, and maybe we did one other. And then we did another conference roll. X is 17. Yep. And so here... your numbers, sorry, someone's going to wonder what I'm doing. You are correct. So this is 12 for me, 12 right here, 424. And so, oh my gosh, what am I doing? This is 424. This is 12. That makes this 0.034. That makes this 0.966. And so those are, we've now identified this is X, this is P naught, and Q naught is 1 minus P naught. So now we just need to go and solve the problem. P hat plus or P mat minus P naught over P naught Q naught over N square root. And this is, we can do around that, square root. And this is equal to a z-score. So let's go ahead and plug in the numbers right here. The sample proportion, the hypothesized proportion, the complement of it. So P hat is equal to, didn't solve it, 12 divided by 424. That is going to be 0.0283. So I'm just write 0.0283. Can you go over some which ones? I'm running out of time. I did do all of them yesterday, I think. I am running out of time though. No. So I think I have a meeting after this. Which ones were you wondering about, Dana? And that was this. And let's go ahead and find the difference right here. So the difference between the two of these, minus 0.34. So negative 0.005698. Negative 0.005698. Good. Oh, no, it's all right. I think it's yesterday's video. I think yesterday's video we did all the quiz problems for today. So I think yesterday's video we did all the quiz problems. No, and please tell me if you can't find anything. Let's see. Who else feels like this whole semester has been a blur? Awesome. No, thank you, Dana. Thank you. No, everyone is so positive, and I really love that. Oh, really? Is this how small it is? I guess. So this number is going to be negative right here. So that's negative 0.646. Because I didn't do the minus to start. Negative 0.646. 646. There we go. That is going to be the z-score right there. And so the question asks, are the conditions met? We need randomly selected individuals. Are they random? Sure. Is it less than 10% of all teenage girls? Sure. And do we have at least 10 expected successes? So we have to do the NP naught. So NP naught is 424 times 0.34. And we have at least 10 expected successes, and we have at least 10 expected failures. So we are good. Write the null and alternative. Test to see if this is what? So is this rate is this the same rate? So which alternative do you think we need? We're asking if it's the same rate. Do you think it's the first one, the second one, or the third one? Because we're asking, is it the same? So if we're asking, is it the same? The alternative should be, is it what? Because the null will be, it's the same. And we're just asking, is it the same or is it what? Because we don't give a preference towards it. We just ask, is this the same for young mothers? Is this the exact same for young mothers? Well, we shouldn't say exact same. Is it possible that it's the same, we should say? And the alternative would be that it's not equal to, because we're not giving a preference. The z-score we found was negative. How many decimals does it want? 2. So negative 0.65. That's what we solved all through there. And we might be able to guess the p-value again. The p-value for this one, since we're doing different, it's going to be pretty large. 3 decimals? It's going to be a hard one to guess. There we go. We got it. Let's go and look at how we obtained that. It was a hard one to guess, though. So to obtain this p-value, you need to go to the David M. Lane. We're shading both sides. Great job, Macy and Dana. Great job. Sorry about that. I was looking down. I was thinking about the p-value, and I was like, gotta figure this out. Gotta figure this out. What was the z-score again? The z-score here is negative 0.65. So we have to graph the outside of this like this right here. And there it is right there. And it gave it to me because I was close enough. But this p-value looks very what? So before we get to the last part, this p-value looks very what for this? Very large or very small? This p-value looks very large or very small? Which of those two? Everyone's been so quiet offstairs. I've been talking to myself, basically. This p-value looks very large or very small? Large. So what should we do? When the p-value is low, reject the null. When the p-value is high, just what? When the p-value is high, just what? When the p-value is low, reject the null. When the p-value is high, just let it fly. Just let it be. Which means fail to reject, and then we don't have evidence to suggest that they're different. So we would fail to reject. We would not have evidence that they're different. And we've done it. We've done the whole homework assignment. So the homework assignment is here in this video for help if you need it. Email me questions if you have it. I will be back. I'll be teaching here in a little bit. But great job, everybody. Keep up the great work. You're welcome, Macy. You're welcome. Have a great day. I'll be back. Email me questions if you have them. Let me know. I'll talk to everyone later. Bye for now.